the beginning again. So last time we saw a bunch of properties, compact operators, and one of them being that there are limits of finite rank, and interpret finite rank operators essentially matrices. And this is really interesting numerically because it means we can approximate those compact operators using finite matrices. Trying to solve a problem, especially a PDE, boils down to solving a sometimes very large linear system. And so the key question here is, say we have some operator k on the Hilbert space, presumably a compact operator, and we have this setup of trying to solve system I minus k x equals y. And note that the reason we have this I minus k is that by default we know that compact operators are never invertible. It wouldn't even make sense to just have kx equals y, but have I minus k, sometimes it works. So on the top you have the full compact operator with some term y and trying to find a certain x. And we're trying to look at the related problem where we have k0, which should be approximation of k, and y0, which should be an approximation of y. And we're trying to look at the solution x0 that we might obtain in the second system and see how close it is to the actuals. Very relevant for numerical application, because we're not only approximating by finite rank operators, but also approximating real numbers using floating point numbers, which are their own approximation issues because they only have finite resolution. So the first theorem on this is that if we have some here not necessarily compact operator but k such that I minus k is invertible, and k0, which should be an approximation of k in the sense that this operation, so k minus k0 times the inverse of I minus k, should be smaller than 1, and really it should be a small number epsilon. Then the theorem says that for every y and y0, are here just y being the true term and y0 being the summation of y, can find unique x and x0 such that I minus k x y, so this is just a standard problem, and I minus k x0 and y0. So this third part also says that I minus k0 is invertible, and in fact it's fairly easy to use from the property that we have on the top. And the third property is that we have a bound on the norm of x minus x0, so true solution that we found, bounded by the norm of I minus k inverse, divided by the I minus epsilon, so epsilon is really small, this is basically 1, times some term that has some epsilon y, again if epsilon is really very significant, and the approximation error between y and y0s. Overall it's a fairly good norm, but note that we have the norm inverse factor which might be very large, so in practice we may have to take a really small epsilon, but it means that we can still get something deep. Especially if we have a small epsilon and some good approximation of y with y0, then our true solution is guaranteed to be small. So all of these are fairly straightforward to, I won't explain them, but you can see on. So this leads to a second term called Galerkin approximation, and Galerkin methods or Galerkin approximation is a term that you see all the time in PD and dynamical systems, because it's really one of the standard way to solve PDEs is to just discretize your system using some kind of basis or some kind of projection operators and solve the projective system and have some proofs that you could go discretize your system as much as you want to get a better precision. Our theorem here says that you have a compact operator on Hilbert space and a sequence of projections that p squared of n is Pn and adjoint, and they have finite rank, but they satisfy also that Pn converges strongly, so pointwise, not in the operator norm, but for any x, Pn of x converges to x. Pn converges to I, the identity operator. Then we have that following operator Pn times k times Pn. So the more what this is that we're first taking our y, approximating using Pn, then solving the approximated problem using k, and then solution of that might again not be in our basis, so we discretize it again using. So the theorem says that Pn k Pn converges in the operator norm k, and so notice that on the top we had that the Pn has to converge strongly, but result is that we have some operator norm burn. And really this is all because k is compact, so by the property we saw last time of k being the compact operator ideal, we know that this k Pn is already compact and Pnk is also compact, so this is a sequence of compact operators. For that we have the operator norm. An example of such Pn and projections is, say we have some orthonormal basis for space, so un, then a standard way to construct the projections would be following fairly straightforward. We saw this in sections. There are other methods, and in fact you don't necessarily need an orthonormal basis. So so you're jumping right into the middle. So as I was saying, so projections you don't necessarily need a proper orthonormal basis. In fact, finite element methods you have that's take a basis that's almost orthonormal but completely, but you still end up with something that's more.
So like a very simple example of this might be like if I'm solving like the heat equation in a Fourier basis.
Yep.
First I chop off the high frequencies, then I apply the heat equation.
Yeah, exactly. Basically,
In that basis, and then I chop off the high frequencies again because a little bit has leaked in.
Yeah, that's exactly basically the canonical example, but you could imagine. So like for the finite element methods, you're discretizing by taking the linear approximations of your function or solution. So by taking these so linear interpolation, you get again a basis that's almost orthogonal, because take one discretization point kind of depends on the discretization points or these neighbors. So it's another way, and basically practice to solve PDEs, you have two big approaches, one being essentially the Fourier basis and the other one being finite elements. And it's, they boil down to the same idea on the top.
I have a bit of trouble visualizing what basis you would use in a discretization like that. I don't think. Can you use Dirac delta functions? I'm not sure that
I
you
will
can.
give an example of that.
Okay.
At the end, I'll draw an example, but remind me in case I forget. So yeah, as brief gets through the proof, I won't go through detail, but the first step is to proving that P and K converges to K. And really it's fairly straightforward because we know that K is compact, so Pnk is compact, and we also know that Pn converges strongly to 1, and so really we can do some manipulations to find that, at least by contradiction, we can prove that, suppose that it is not converged, then okay, we can find some epsilon such that Pnk minus K larger than epsilon, which means that the supreme norm is epsilon, and so with some terms we can construct a sequence x and k such that x and k's are more than 1 in norm, and that the p and k's k minus k, x and k's are larger than epsilon in norm. So we have a bounded sequence, but we have a bounded sequence, and so there has to be a subsequence x and kl such that the sequence k and kl has to converge to some y. So if we check that into assumptions, we have that something that epsilon has to be smaller than this expression, which expands into something that converges to 0. And so we have a contradiction. And really, this schema is basically the same that comes up in the proof, in that we assume that it's not convergent and construct a subsequence that should converge. And
There has to be a better notation for like nested subsequences.
I mean, there kind of is. I've been reading about. Sorry. At one point for the later proofs, I have a slightly better notation, but there's actually like a super powerful tool called an ultra filter, which is basically like the super-powered, very abstract tool to like make this proof, but without having to take the sequence recursively. But that's really outside of the out of the topic. Anyway, the second and first step of the proof are to show that KP and K, and actually both of these are just immediate from the first one is just K is compact, so the K adjoint is compact, and so P star K and star is equal to P and K star, and so it converges to K star by the first property, and so it's out. And the last one is just together we what my analysis professor called hocus pocus, because we get from the first part to the next part, we have to add I think we have to add like this P and K. You have to add something and take it away at the same time, and so for the triangle identity, you have something that converts to 0 and 0, so it all converts to 0, so we're good.
I think putting either term in the middle could work.
Yeah, you could have done it. I've already mentioned a lot of my comments on the bottom, but one thing is that, especially for PDEs, quite often the solution operator, which I'm denoting with very big quotes here, exponential of AT, A being imagine dx per dt being A, where A is an operator xt. So the solution from, if you imagine from standard dynamical system, the exponential of AT, but the exponential operator has a bit tricky to define in some case, but in this case it's actually a compact operator. So it means that we are guaranteed to have a good approximation of this. And I'll actually go back to this example. Okay, so we're actually moving on to the spectral theorem for compact operators. So we're done with the approximation, but come back for the the last part. As a brief reminder, so recall that the spectrum of an operator from one space to space is defined as the set of complex numbers lambda such that lambda I minus t not invertible operator and can be invertible or not. And it's basically a generalization of the eigenvalues and eigenvectors that we have in standard. And in particular, it's a bit more complex because we have the point spectrum, which is really eigenvalues because you can find vectors x such that dx is equal to lambda x. In general, it can be a lot more complicated and be a bit of a nightmare. But we saw in previous chapters that self-adjoint operators, so then spectrum has to be real, so fed into the real numbers, and the eigenvectors have to be orthogonal. So if you add to that the fact that we have compact operators approximatable by finite rank operators, we can put this all together into essentially being operators that we can diagonalize. It's not all operators that can be diagonalized are self-adjoint and compact, but at least for self-adjoint and compact we have a really nice theorem. Have self-adjoint operator in a Hilbert space, which is also compact, with infinite rank. Then there exists some orthonormal eigenvectors and eigenvalues, such that limits of the eigenvalues tends to equal to 0. Note that 0 may or may not be an eigenvalue itself, but at least we have definitely a point spectrum consisting of these lambdas, and the rest of the spectrum is either only the lambda and 0, and 0 may or may not be an eigenvalue. So have the point spectrum and 0, and sometimes 0 is an eigenvalue, sometimes it's not. So the last property is that dx, x in space, is essentially what you'd expect being the sum of the lambda k's times it should be sum of the lambda n times the projection of x on space of un times un. So essentially what you would expect from a spectral decomposition. Nothing, but note that really this says, okay, it's for each x, so you might assume, oh, it's only strong convergence, but really from everything we saw before, can really say that the operator is simply the sum of lambda n and n, so where this is just the like the not the lambda, but the anonymous function that waits an x and returns the projection of x on. So really we have the operator convergence for. Okay, so before actually trying to prove this, we can make a few observations and a few lemmas. We already have real eigenvalues in orthogonal eigenvectors, 3 because that's self-adjoint operator. And furthermore, we know that any eigenvalue in eigenvector, essentially the eigenvalue absolute value has to be smaller than the norm. And we can take a first lemma that says if we have a self-adjoint operator, then the norm, a Hilbert space, norm is the supremum of all x having norm 1 of this expression being the absolute value of inner product tx with x. It's actually very easy. The second I give a proof because it's a bit more. If we have again a self-adjoint compact operator, then either the norm of t or minus the norm eigenvalue of the. Really, for this, use the previous lemma, find some kind of sequence or subsequence of x unit ball, such that this product here converges to. So then for each of those you have either that. Yeah, so the product xn is plus or minus the absolute value. So from that you take the limit and you essentially have that norm of t minus the norm is an eigenvalue. You can even find either the convergence or y explicitly. But yeah, last part you have your sequences that converge. So you find y explicitly that serves as the eigenvector in the. And so the final lemma before the main proof is a result about, again, a self-adjoint operator. If you have a t-invariant subspace Y, so t-invariant just means that t applied to any element of Y stays in Y. So it's very easy to prove this, that all complement of Y is also t-invariant, and also that the projection on the orthogonal complement is also self-adjoint. Very straightforward. So also that if T compact, then the projection restriction is also compact. It will be actually immediately. So using all of these, we can actually prove the main theorem that, and the idea for this is to essentially decompose our operator one eigenvector and eigenvalue at a time. Start from h1 being h and t1 being. Then by the second lemma, we can find lambda 1 and 1 such that the absolute value of lambda 1 is t1. In this case is the if we actually have found the largest eigenvalue, you have one. Then for the next step, we take h2 being the span 1, but with the orthogonal complement of that. And by the third lemma, this has to be a closed t-invariant subspace, and so we define t2 being the restriction on space. It's a self-adjoint and compact operator. Again, find lambda 2 such that absolute value of lambda 2 is. And so we found the second largest eigenvalue, and so the idea is to continue doing so. First find the largest eigenvalue on your subspace, then only consider the subspace that does not contain this eigenvector and an eigenvalue, and keep going until you find the end. By here we have to actually use the fact that our operator has infinite rank, which means that this process continues and as n goes to infinity, and so we end up with an infinite sequence of eigenvalues and eigenvectors, which is also decreasing in this, that the absolute values of the eigenvalue, so absolute value of lambda n has to be smaller than the one that came, or equal ones that came before it, to have a sequence of eigenvectors and eigenvalues. So since we know that the absolute value of n is decreasing, has a limit being the infimum, and let's call it epsilon. So if we suppose that epsilon is greater than 0, then we can again do the same idea of constructing a bounded sequence that from this hypothesis will be bounded, so larger than squared. But T compact again, we can find convergence and hence again, we have the contradiction. So we have that the absolute value of lambda n 0, lambda n goes to. So the final part here is to actually look at the version since actually because we take the difference between two by taking ETN. We take the of x minus our expression, or moving the first n, so yeah, the first n minus 1 eigenvectors. We're left with Tn being the restriction on the rest. So we can expand it. I think it's the Cauchy-Schwarz identity. About the product, and we have term Tn and minus x minus sorry, the so the not the truncation but the rest of the truncation. So Tn, we know that the has to be smaller than lambda n. This has normal x, and so have something that's smaller than lambda n times x, a constant, so it has to go to. I have actually basically the canonical example as I mentioned. If we consider the heat equation, which is pretty much the standard PDE that try, being d equals to the Laplacian times u. Here, if we assume more finite dimension, one dimension, just the second derivative. And note that we do have to make some assumptions here. First of all is that, okay, we assume that we have a bounded domain of length L. And we need to also assume that we have some initial condition u x 0 being f of x. And there are some conditions on x that we get in details. And we also need boundary conditions telling us, okay, what happens at the ends of my domain. And for this, you can imagine that domain is really a metal bar that maybe might be getting heat at one end, and you want to see how the evolves. So here we're saying that the heat at both ends has to be 0 for all times. And this second is important because it's a way to make sure that U's are in fact in a Banach space, because if you assume arbitrary conditions, might not have a 0 solution as your space, and so it's actually important. Notice that you can interpret this as essentially a linear differential equation, because the Laplacian delta is a linear operator. Note that it's not bounded, and it's a bit different than previously, but it's also is defined on a dense subspace, because of course now the function can be differentiated twice. You need to actually derivative to exist, and really the domain of this operator is not the full space, but at least a dense subspace, because you can approximate any function with twice their differentiable function. And it's well known that we plug the Fourier basis in Laplacian. Here we've scaled it a bit, so sinus of n pi x divided by L. This gives us essentially an eigenvector of operator, because we have minus n squared pi squared by the L squared times our original function. So we know that the Fourier basis, which is here, we also know that it is in fact a basis of eigenvectors. So these are the eigenvectors of the Laplacian. But as mentioned, sorry, notice that these eigenvalues are not bounded. n squared term that goes to infinity, and so we have a basis for eigenvectors, but the operator is bounded. But however, the solution operator, again the exponential of d delta, satisfies. So we can explicitly write the solution as a sum of dn sinus, so our eigenvectors times e to the minus dn values. Notice that this now is really bounded, and like it goes to 0, and so you can interpret it as saying that this solution operator is compact, and it is. And dn, which is really the Fourier coefficient, you squint at it for long enough, it really looks like just projecting the initial condition f on our basis. So really we have some nice result about the of our PD being boiling down to just we've just approximating a compact operator. This is a very nice perspective on the basis, or at least either the Haidt equation or Fourier, and a very standard one in vector field. You can also find some other types where instead of differential operator, you have integral operator. I managed to pick it without scuffing my lungs out, but so you wanted to hear about the other types of discretization.
Yes, please.
Okay, let's the rough idea is that, say you have or domain L, and you discretize it by simply taking equidistant. I should have principle. The idea is that you discretize your domain. Say if my true function initial condition f. Did I forget now?
You're selecting a tiny box in the middle of your screen somewhere.
Yeah, I
You
see.
got to deselect it, otherwise you can. Yeah, there you go. Well, no.
Oh, yeah, it's really doing this. Select.
Select none. Yeah, there you go.
Yeah, it's a bit tricky. So
That's
let's
a good.
assume that the function f looks something like this. So this is my true function, and what we do then by taking the discretization points is that instead look at the value of the function at the discretization point. And sometimes you can also interpret the base one would just be assuming that we're linear interpolation of piecewise linear function. But you can take some higher orders. So then when you express the the second derivative on discretized object, it's really a finite difference. So for example, have usually have like some there's like a u of fxx. So second derivative is a bit of a notation. You usually say that it's I remember it should be above I think it's x minus 1. Let's start from the derivative. So say we were trying to approximate the derivatives. It's about x minus x minus 1 divided by h. So h would be our time step or discretization step. So this is really the finite difference. Secondary kind of abusing notation. So once we approximate the secondary, we can do essentially impose the finite difference of the derivative on top and also take it to z plus 1 minus z and combine both, and we have something like derivative x. Then we have to take h squared as the discretization step.
Well, you end up with an h squared, but
Yeah,
you just start with an h in the first step, right?
yeah. And if you
Yeah.
expand this, you basically get something like u of z minus 1 minus
Yep.
if you've done anything with like graphs, you might know the graph Laplacian, which is basically the so if
Yeah,
you
this much I remember.
yeah so the you express the if you look at it in terms of matrices, this basically defines a tridiagonal matrix.
Mhm.
The so the discretized Laplacian looks like try that have like -2 on a diagonal, and then the have a matrix that has -2 on the diagonal and then 1 on the side. I have to scale it. So this is an example of a basis because you can imagine that these the way you've built this discretization, you can also imagine that as products of f with functions. Well, what these functions look like. Imagine taking basis function in this form.
Okay, so my basis functions are basically these sawtooth functions, which are kind of
Yeah,
the closest linear approximation to the Dirac delta
yeah. But
width of
really,
the
so the fact that
discretization.
slopes,
Okay.
it means that if you look at
Yeah,
the
yeah.
next to it, it has an overlap, and so because of this overlap,
Right.
you have a matrix that is not fully diagonal, as it would be in the Fourier case. So this is an example of a basis that is not completely orthogonal, but still end up with some nice structure because trigonal matrices are really nice numerically. Because you can, like, if you want to solve these problems, trying to find and the u equals f, then this is fairly easy because there are so ON algorithms for solving this kind of system.
Right, right. But we didn't actually assume that the Galerkin approximation had to use an orthogonal basis, we
No,
can just pick any basis to project onto.
no. Really, so if you can use like a Fourier basis, it's great, but it really
Yeah.
depends on the domain. So for simple
I
domains
assume you
like,
can only do that in like very idealized cases.
yeah, basically if you're on a nice domain like a line or maybe a box, then it's easy to use Fourier. But say your domain is like some very complicated shape, then it's a lot more tricky to actually find these Fourier approximation, and so it's kind of for that reason that for that application where have some very complex shaped domain, you instead discretize it using this kind of approach. Uh, then it's the finite element method. Discretize in this way, and hopefully, usually the way it works is that because you have functions that are only overlapping for neighboring points, the matrix you end up with is very sparse, so it has quite a lot of
Yeah.
zeros. So that's a structure that you can use. But this is more into getting more into numerical analysis. Yeah, I think this is basically the simplest example I could give.
Cool. This was exactly what I was looking for.
I remember I saw like you can also prove some results about the kind of realizations where you want to say that your space, like your discretized space, converges in some way to the the limiting space or the real space, and you also have some pretty strong results saying, okay, if my discretization converges and have some other properties on the operators, then you basically have that the operator like the discretized operators converge, their spectrum converges, and the eigenvalues also eigenvectors also converge
Yeah.
nicely. In fact, I think this sort of lies like if you've ever heard about diffusion maps, which is actually more from the machine learning side, where you have some points in some space that you assume come from a manifold, and you're trying to recover the manifold, you have some pretty strong results about how certain methods can in fact approximate a Laplace operator on manifold. So again, you can recover the eigenvalues and eigenvectors. In a sense, you really do find the eigenvector, the manifold.